If I want to represent 0 to 9, how many bits I required? I required 4 bits. 2 to the power 2, it is 4, and 2 to the power 3, it is 8. So here BCD representation is nothing but 8, 4, 2, 1. If I go with ASCII, it supports only 128 characters. And if I go with UNICODE, it's going to support wide range of characters. Hello to all, a warm welcome to my new session on number system. I am Revati from the Department of Computer Science, Vidhyaashram, First Grade College, Temple of Excellence, MYSURU. So dear student, before going to start my today's session, let me to recall the topics which I have covered in my last session. There I started with decimal number to hexadecimal. That means how we can able to convert decimal number to hexadecimal number. Along with that, I have covered hexadecimal number to decimal conversion. Along with that, binary number to octal number conversion. Along with that, octal number to binary number conversion. Along with that, I have covered binary number to hexadecimal numbers. These are the 5 topics I have covered in my last session. But dear student, in my today's session, at the beginning, I am going to deal with hexadecimal numbers to binary numbers. Along with that, how can I convert octal number to hexadecimal number? Along with that, I am going to deal with how can I convert hexadecimal number to octal number? Along with that, I am going to deal with computer codes. These are the topics I am going to deal in my today's session. Now, at the beginning, I am going to have conversion from hexadecimal number to binary. So, I have hexadecimal number and I want to convert that to binary. Now, what I will do here, I am going to extract individual digit from the hexadecimal number and I am going to write the binary equivalent for that, and at the end I am going to club all the bits together. Now see here, I am going to have the hexadecimal number, that is CEBA. So here A is nothing but 10, B is 11, 13 and 14. So what I will do, I am going to extract individual letter separately and I am going to write the decimal equivalent. Now I am going to write the binary equivalent for that. If I consider 12 divided by 2, 2 6s are 0 remainder, 2 3s are 0 remainder, 2 1s are 1 remainder, and I am going to write 1 1 0 0. So 1 1 0 0. And for my next letter, it is E, that is nothing but 14. And I am going to find the binary equivalent. And my next letter, it is B. It is nothing but 11 and I am going to write the binary equivalent, and at the last I am going to have A. A is nothing but 10 and I am going to write the binary equivalent, and at the end I am going to club all the binary bits together. So I will write 1 0 0 1 1 1 0 1 0 1 1 1 0 1 0, and it is nothing but the binary conversion of given hexadecimal number. Moving further, I am going to have Conversion from octal number to hexadecimal. I have octal number. Now I want to convert that octal number to hexadecimal number. So using binary system, we can very easily convert octal number to hexadecimal numbers as well as vice versa. So dear student, first write the binary equivalent for each octal digit. First, what I want to do, I want to write the binary equivalent for each octal. After that, I want to regroup. That means while regrouping, I'm going to consider 4 bit together because I want to consider octal number to decimal. Octal means what? It is 2 to the power 3. That means in octal number, I can able to get only 3 bits, and if I go with hexadecimal number, I can able to get 4 bits. That means I'm going to make a group of 4 bits together. Now let me to consider the example here. Here I have 274. So what I will do, I'm going to extract individual digits separately. So I'm going to write 2, 7 and 4. Now I'm going to write the binary equivalent of this digit. Now 2 is nothing but 0, 1, 0, 7 is nothing but 111 and 4 is nothing but 100. Now I want to convert this into hexadecimal form. So what I will do, I'm going to write the binary digit as it is. So dear student, now I want to make a group and each group holds 4 bit. Now I will make a group here. So 4 bit. Here I have only 1 bit. To make it 4, I'm going to add 3, 0. Now I'm going to write the hexadecimal numbers for this binary number. So here it is nothing but C and here it is nothing but B. B is 11, it is 12 and here it is 0. Now the conversion of 274 equal to B.C. It is hexadecimal number and this is my octal number. Now, dear student, I'm going to have conversion from octal number to hexadecimal number. So here I have octal number and I want to convert that to hexadecimal. So what is the step? First, write the binary equivalent of each hexadecimal number. First, what I want to do, I'm going to have the hexadecimal number and I want to write the hexadecimal number first and I want to write the binary equivalent of this hexadecimal number, and while grouping, I want to group 3 bits together in order to get my octal number. So this is the way I can able to convert hexadecimal to octal. Now, see, this is the example I'm going to have here. So I have F, A, D, E. First, what I want to do, I want to write the decimal equivalent. E is nothing but 14. 13, A is nothing but 10. It is 15. So F is nothing but 15, A is nothing but 10, D is nothing but 13 and E is nothing but 14. And I'm going to write the binary representation of these digits. So this is my binary representation. Now dear student, I'm going to write all the bits together. Now according to the rule, I want to group and each group must have 3 bits. So I'm going to group 1, 2, 3. It is 3, 3 and 3. To make it 3 bit, I'm going to add 2 zeros at the end. Now I'm going to write the octal equivalent for this binary bit. So here it is 6, here it is 3, 3, 5, 7, 1. Now for the given hexadecimal FADE equal to the final result here is 175336. This is nothing but the octal representation of given hexadecimal number. Now dear student, I am going to have binary coded decimal. So this is nothing but the computer code. Now dear student, tell me why I required computer code. So what is the need of computer code? So dear student, as we know that computers are able to understand only instruction, and whatever the instruction we are going to provide, that is in the form of machine language, that is nothing but binary code, that is zeros and ones. Now, whatever the instruction I am going to provide to the computer must able that instruction. For that reason, I require computer codes. For example, think that I am going to type hi. Now tell me how the computer is going to understand this is hi, because when I press H, that H is converted into ASCII code. Then that is given to the computer system so that computer can able to understand which letter is typed. For that reason, I required computer code. And when I talk about computer code, we are having BCD, that is binary coded decimal. Along with that, I am having ASCII code, along with that UNICODE, etc. But at the beginning, I am going to have binary coded decimal number, or it is nothing but BCD number. So what is this BCD number? What is the need of BCD number? If I consider digit, I can able to have 0 to 9. Okay, fine. Binary coded decimal number system is a number system in which decimal numbers are represented from 0 to 9. Suppose if I want to represent any decimal numbers, I am going to use decimal number system, that is 0 to 9. And if I want to represent 0 to 9, how many bits I required? I required 4 bits. For example, think that if I have 8, to represent 8, I required 4 bits. If I consider 7, to represent that, I required only 3 bits. But in binary coded decimal, I am going to use 4 bits, and it is called BCD. Now, I will tell you, dear student, just remember here that I have the digit called 9, and I am going to divide this digit by 2. 2 fours are 1 remainder, 2 twos are 0 remainder, 2 ones are 0 remainder. Now it is 1001. That's nothing but 4 bit. Now each bit of BCD number has positional weight. So dear student, if I consider BCD numbers, it has positional weight. That means the 0th position will have weight 1, first position 2, then third position it is 4, next position it is 8. So 8 plus 1 it is 9. So in BCD each position has weights. The weights are assigned as per the position occupied. So weights are assigned as per the position occupied. The weight of the first position is 2 to the power 0. So dear student, let me to clear the board first because I want to explain further points. For that reason, I am going to clear the board first. So dear student, let me to consider the example here. Think that I have 12 and this is my decimal number, and if I divide this number, I'll get 2 6 are 12, 0 remainder, 2 3s are 6, 0 remainder, 2 1s are and 1 remainder. Now I'll get 1 0, that is 1 1 0 0. And if I write the weight according to the position, it is 2 to the power 0, it is 2 to the power 1, it is 2 to the power 2, it is 2 to the power 3. 2 to the power 0 means what? By the mathematical property, 2 to the power 0 is 1 and 2 to the power 1, it is 2, 2 to the power 2, it is 4, 2 to the power 3, that is 2 into 2 into 2, it is 8. And if I want to get 12, which are the digit I want to add? That is 8 plus 4, it is 12. So I'm going to write 1 1 in the place of 8 and 4, and for the rest of the position, I'm going to write 0. And this kind of representation is known as binary coded decimal numbers. So the rightmost position is 2 to the power 0, that is nothing but 1 by the mathematical property, and 2 to the power 1, it is 2. 2 to the power 2, it is 4, and 2 to the power 3, it is 8. So here BCD representation is nothing but 8 4 2 1. Hence binary coded decimal number system is also called 8421. So here BCD number system is also once again called as 8421. Now if I consider 4-bit BCD number, then I can able to have only 16 configuration, that is 2 to the power 4 equal to 16 configuration, and it is insufficient to represent all the characters. For that reason, I am going to have 2 to the power 6, it is 64. So I am going to have 64 configuration so that I can able to represent all the character. So here we are having 64-bit BCD so that I can able to get 64 character, and this is the conversion I'm going to have. That means I'm going to have the decimal numbers. For that, I'm going to write the binary representation and I'm going to club all the result together. Moving further, I'm going to have the table representation. So dear student, please remember this table properly, that I'm going to have the decimal number 0 to 7 and I'm having the binary number, that is 0 to 7. And if I consider BCD, same 0 to 7 I have. Now for 8, binary number 100, and for BCD it is 100, and for 9, 1001, BCD 1001. And if I go with 10, in binary it is 1010, that is 10 divided by 2, 2 5s are 0, 2 2s are 4, 1 remainder, 2 1s are 0. So it is 1010. So this is my binary number. And if I consider BCD, I have 10, and now I'm going to write the BCD code for individual digit. In 10, first I'm going to consider the 0 and I'm going to write the binary representation, that is 0, 0, 0, 0. And if I consider 1, it is 0, 0, 0, 1. So here for 1 it is 0, 0, 1 and for 0 it is 4, 0. And if I consider 15, in binary I have 4 ones. If I go with BCD, I'll write 15. Now I'm going to extract individual digit. Now I'm going to write the BCD representation. First I'll take 5. So it is 0, 1, 0, 1. And if I consider 1, it is 0, 0, 0, 1. And if I consider the table 0, 0, 1 and 0, 1, 0, 1. This is the way I can able to represent BCD numbers. Now I'm going to have gray code. So dear student, the gray code is non-weighted coding system. If I consider BCD or binary decimal, all the things comes under weighted coded system. And if I consider gray code, we don't have any weight because we are not going to bother about the positions as well as weightage of each position. And it is cyclic as well as. So here BCD code is nothing but the non-weighted code and it is cyclic. And it is referred as cyclic because the successive code word in this code differ from only one bit position. It is cyclic means I'm going to consider each successive bit for each calculation. So it is a unit distance code. It's also known as unit distance code and it is reflective. And in many practical applications such as analog to digital conversion as well as unit distance codes are used, where we can able to find the use of gray code in the field of analog to digital conversion. In that time we are going to use gray code. Now let me to consider the example here. I have 1, 0, 0, 1. To perform gray to binary, I have to perform XOR operation. To perform XOR operation, I want to consider the table. So I have 4 possibility and 2 input 0, 0, 0, 1, 1, 0, 1, 1. And I'm going to get high output only when my both the inputs are vary. So here if I consider this one and this one, I'll get high output and remaining it is 0. And this is the truth table of XOR gate. Now I want to perform XOR operation. So I'll get the result 1. It is 0, 0 and I'm going to write 1 as it is. Now if I consider another example, okay, I'm going to perform XOR. It is 1. It is 0 and I'll write 1 as it is. This is the way I can able to get gray code. Now moving further, I'm going to have the ASCII code. So what is this ASCII? That is nothing but American Standard Code for Information Interchange. So this is also standard and it's also known as American Standard Code for Information Interchange, and it is used to represent number to text. So it is mainly used to represent number to text. For example, if I have any digit that is represented in the form of text. So here digits, that is 0, 1, 2, 3 up to 9, letters, capital letter A to Z or small letter A to Z, and symbols, that is exclamatory symbols or semicolon, any special symbols are called character That means in ASCII, digit, letters as well as special symbols are called characters. So dear student, when there is a piece of text, then ASCII converts each character to a number. For example, say I have A, B, C. I have A, B, C. And in ASCII table, for small letter A, it starts from 97, B 98, C 99. And when I write or when I type A, it is converted into 97, B, it is converted into 98, C, it is converted into 99. So whatever the text I'm going to enter, that must be converted into numbers, or whatever the character I'm going to type, that must be converted into numbers, and it is known as ASCII representation. This set of number is easy. That means ASCII numbers are very easy to store in the computer memory. So it assigns numbers to any word or any character is known as encoding. So if I consider this example, I have A and I'm going to assign 97 to A, and it is known as encoding. So simple words assigning a number to character is called encoding. The example here is, if I have capital letter A, then I can able to assign 65, and ASCII uses 7-bit to represent a character. So here ASCII uses 7-bit to represent a character. That is nothing but 2 to the power 7. It is 128. So what is ASCII? It's mainly used to represent character to number. And how many bit representation? It supports only 7-bit representation. So it represents maximum of 128, that is 27 characters. Now Unicode. So what is this Unicode? I know ASCII code, but what about Unicode? So here the Unicode is maintained by UNICODE consortium and covers a wide range of characters. So here Unicodes are responsible for covering a wide range of character, and it contains representations for letters in languages such as English, Greek, Arabic, etc. That means in Unicode, I have letter to represent other languages such as English, Greek as well as Arabic, etc. Along with that, I can able to represent mathematical symbols, emojis, and many more. There are 3 types of Unicode, that is UTF-8, UTF-16, UTF-13. And if I go with UTF, then it uses 8 bits. Suppose if I have any character and to represent that, it's going to use 8-bit representation. And if I go with 16, it uses 16-bit character, and if I go with 32, it uses 32-bit for a character. In UTF-8, the first 128 characters are ASCII character. That means if I go with UTF-8, the first 28 characters are ASCII character. Therefore, ASCII is valid in UTF-8. Unicode is used in internationalization and localization of computer software. So dear student, most of the computer softwares are going to use Unicode for their internationalization as well as localization. And this standard is also used in operating system. Along with that, extensible markup language, along with that .NET programming framework and other programming languages like Java. So here UTF-8, that is make use of ASCII code. For that reason, it's mainly used in the operating system and it is also used by the many computer softwares along with that programming language. Now, I'm going to have the difference between ASCII as well as Unicode. And if I consider ASCII a character and encoding standard for electronic communication. That means ASCII is nothing but the character encoding standard for electronic communication. And if I go with Unicode, a computing industry standard. So it is a computing industry standard for consistent encoding. So it is a industrial standard. But what about ASCII? It is nothing but character encoding standard. Now, ASCII stands for American Standard Code for Information Interchange, whereas Unicode stands for Universal Character Set. So, Universal Character Set is known as Unicode, whereas ASCII is nothing but standard for American Standard Code for Information Interchange. And if I go with ASCII, it supports only 128 characters. And if I go with Unicode, it's going to support wide range of characters. And if I go with ASCII, it uses 7-bit to represent characters. If I go with Unicode, it uses 8-bit, 16-bit and 32-bit depending on the Unicode type. So dear student, if I go with Unicode, it uses 8-bit, 16-bit and 32-bit character representation. And if I go with ASCII, it requires less space. And if I go with Unicode, it requires more space. Now, dear student, in my today's session, I started with number conversion along with that computer code. In that, I had completed binary coded decimal number, gray code, ASCII code as well as Unicode. And from the examination point of view, computer codes are very, very important. Now, dear student, let's meet in the next session with the new topic called types of computer. Until that, dear student, keep watching and keep learning. Thank you.